All right, we're going to go over the last year's exam 2. I made a copy of the exam here and labeled it key, so we're going to go over that. Remember that your test is probably going to be a little different because of it being in a fully online fashion. All right, so the first question on the exam here is about the conservation of mass, and the idea is the mass of the reactants is going to be equal to the mass of the products. So you know that you have 65.4 grams of zinc, and it consumes 72.9 grams of hydrochloric acid. And then we know that we produce 2 grams of hydrogen gas, but we don't know how many grams of zinc chloride are formed. So 72.9 plus 65.4, that's going to be 138.3 grams. If I subtract from it the 2 grams there, that's 136.3 grams, and that must be the mass of the missing zinc chloride, so 136.3 grams. And again, that's supplying the law of conservation of mass. Very important law. Oftentimes we kind of ignore the fact that we're using it, but really without it, chemistry wouldn't exist. All right, so we've got a table here where you're going to go in and you're going to figure out protons, neutrons, electrons, charge, mass number, and name. And again, this is in a situation where you didn't have access to, Google, which is unfortunately a big advantage. The name of K is potassium, and usually potassium, Potassium, and then P is phosphorus. And usually they're put together because, K doesn't seem to make sense that that's potassium, which starts with a P. So people are confused about that. Silver is Ag, from the same root of the word that gave us Argentina, which is the land of silver. Gold is Au. So those are 2 elements there. Now, the name and the symbol gave us the number of protons. If we look on the periodic table, we can see that potassium has got 19 protons. That's its atomic number. And that phosphorus has 15 protons. And that silver has 47 protons. And that gold has 79 protons. Now, to ask this kind of question in an online environment, I'm probably just going to leave the name and the symbol off and give you protons, neutrons, and electrons to deal with. All right, so the mass number is just the sum of the protons plus the neutrons. So if I have 19 protons and 20 neutrons in my potassium, that's 39. If I have a mass number of 31, and 15 of those are protons, then I must have 16 neutrons for phosphorus there. Silver, I've got 47 protons and 59 neutrons. So that's 46 plus 60 if I move one over, which makes it 106 mass number. And then with gold here, I've got 79 protons, 199 mass number, so I must have 120 neutrons. And then the electrons and the protons are equal to the charge. The charge is the protons minus the electrons. So if I have 19 protons and have a charge of +1, I must only have 18 electrons. If I've got 15 protons in phosphorus and 18 electrons, I'm going to have a charge of -3. If I have 47 protons in silver and 47 electrons, that is neutral. That's a charge of 0. And then gold, I have a charge of +3, which means I have 3 less electrons, 76 electrons. Now, knowing the regions of the periodic table, we're going to match up the sections here. Krypton is a noble gas. Barium is an alkaline earth metal. It's in column 2. Palladium is a transition metal. Bromine is a halogen. And sodium is an alkali metal. We're asked to pick who's going to behave most like nitrogen. What we're going to look for is who's in the column with nitrogen. So nitrogen has phosphorus, arsenic, example going down the column there, and there's phosphorus. Phosphorus is going to be most like nitrogen. What that means is that, if there's a compound called NH3, and that is called ammonia. There's a compound of phosphorus and hydrogen that's pH 3. That's what we mean by most like. It behaves similar. Okay, indium exists as 2 isotopes. We've got 49 protons and 64 neutrons. So indium element is In. 49 protons is the thing that goes on the bottom. The top is going to be the mass number. So 49 plus 64 is the same as 50 plus 63. That's 113. And 49 and 66 is the same as 50 plus 65. So that's 115. Those would be our 2 isotopes of indium. Now, in this case, we got 2 isotopes where we've got a mass of 13.001, that's 74.35% abundance. The other's mass is 14.07. So the first thing I got to figure out is what's the abundance of the second one, right? So if 13.001, this is the mass, this is the percent abundance. So set 13.01 is 74.35, 14.007. This is going to be 100 minus 74.35 if those are the only 2 isotopes. So that's going to be 25.65, I think. Now, I think when you're doing calculations with these, I recommend that we convert percent abundance to abundance, which means that we move the decimal point to the left twice, drop the percent sign, and so we'd express these as these 2 numbers, 0.7435 and 0.2565. Our mass is then going to be, we always say that the mass, the average atomic mass, AAM, is the sum over all the isotopes of the abundance times the mass. It's our summation notation. That big symbol there, of course, is the sigma. That means sum up. So what that means is we're going to say, okay, I've got first isotopes 13.01. We got 0.7435 abundance of 13.001. And then I'm going to sum the next term, which is 0.2565 abundance times 14.007. So if I had to guess, this is probably going to be about 3/4 of the way between 13 and 14. So if I get something around 13.75, I'm not going to be shocked. All right, so I'm going to use the parentheses on my calculator to make this an easier calculation. So 0.7435 times 13.001, close that parentheses, and then add to it and open up another parentheses, 0.2565 times 14.007. Close that, and I get 13.25. Okay, that seems wrong. But let me think about that. No, I guess that's right. I'm sorry. I was thinking that it's going to be, since it's 3/4 of 13, it's going to be 3/4 of the way from 14 to 13. So 13.25. I should probably claim I've got 4 sig figs here. I've got 5 sig figs here. I can claim, I think, 4 sig figs. So I'm going to claim 13 0.26 is my average atomic mass there. All right, so just general trend. As the wavelength increases, the frequency is going to go down and the energy is going to go down. We're asked to calculate the frequency and energy of a 450 nanometer proton. That is the wavelength. You had to recognize that. So for the frequency, nu is going to be c over lambda. That's 3 times 10 to the 8th meters per second. 450 nanometers, I'm going to write as 450 times 10 to the negative 9 meters, where nano is the 10 to the negative 9. So 3 second comma 8 divided by 450 second comma negative 9. Now let's think about this just a second before I hit the enter sign. So 3 over 450, well, let's think about that as 3 over 0.45 for a second. If it was 3 over 0.45, it's going to be about 6. Now, to make that 0.45, I'd have to multiply 10 to the negative 9th by 3. So that make that 10 to the negative 6. 10 to the 8th divided by 10 to the negative 6 is going to be 10 to the 14th. So I'm thinking 6 times 10 to the negative 14th is my answer. And I get 6.67 times 10 to the negative 14th. And meters cancels out and the units are seconds to the minus 1 or hertz. So 6.67 e negative 14 seconds to the minus 1. For the energy is equal to Planck's constant times frequency, so 6.626 times 10 to the negative 34th joule seconds, and 6.67 times 10 to the negative 14th reciprocal seconds. Seconds cancels out, and so that's going to be something like 36 times 10 to the negative 48th, or 3.6 times 10, or probably 5 times 10 to the negative 47th. I got that one wrong. Oh, that's because I wrote this wrong. It's not negative. This is positive 14, so that's my mistake. This is positive 14. That's positive 14, so this should be positive 14. So instead of dividing, instead of multiplying by positive 14, I multiply negative 14. That's just an error of 10 to the 28th. Not the sort of error you want to make when you're, say, calculating your dosage for a patient. I know that I sometimes make those errors, so I know that something is amiss. And again, the fact that I had calculated it, I got something that looked different, forced me to think about, okay, what's going on? So 4.42 times 10 to the negative 19th, and the units are joules. So 4.42 e negative 19 joules would have been my answer there. All right, so what happens when you go from n equals 1 to n equals 5 level in the Bohr model? A photon has to be absorbed. You have to put energy in to go up on the Bohr diagram. You're going to write the electron configuration of sodium. So that's going to be 1s2, 2s2, 2p6, 3s1. We're asked who has the configuration argon 4s2, so that is going to be the calcium ion, and obviously the first question is probably not one, 14 is probably not one I'd ask you in an online environment. 15 I might ask you that. That's probably a better way of doing it. 16, again, I might give you a filled orbital diagram and ask you to tell me which element it is. Not the other way around. So with iron, we got 26. So we're going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then we go over here to the 3Ds. So 20, 21, 22, 23, 24, 25, 26. And then for O2 minus, I recognize that oxygen picks up 2 electrons, so it's isoelectronic with neon if it's 2 minus. So that's 1s2, 2s2, 2p6. And then if we look at things that are isoelectronic with argon, the chloride minus, the Cl minus 1 or chloride ion is going to be isoelectronic with the argon. The potassium ion is going to be isoelectronic with argon. Sodium and fluorine are going to be isoelectronic with neon. Calcium plus 2 is also going to be isoelectronic with argon for that question. Asked to describe the different models of the atom we talked about here. What are the different models? What evidence caused him to adopt each new model? Basically the Greek atom was basically, it was indivisible. And the Greeks didn't distinguish between elements, and I really wouldn't draw an arrow straight from that to Dalton's atom. There obviously was a long period of time and a lot of time when nobody thought about an atom. What made the Dalton's atom, what the ideas were things like the law of conservation of mass, to explain where, how matter was tracked through a reaction, breaking things into atoms and tracing them through, were there. There was the law of constant composition or definite proportion, which said that, water is always H2O, for example, and then the law of multiple proportions, which said things like if you have 2 different compounds of the same elements, that there'd be a whole number ratio. So, for example, H2O and H2O2, which is hydrogen peroxide. In the H2O2, we have twice as much oxygen as we do relative to hydrogen in H2O. That's what the law of multiple proportion basically says, is that kind of stuff. Now, Dalton's atom and Dalton's atom, all of one element, were the same, and they never changed. Okay, and it turns out that that's wrong. There's isotopes where you have different number of neutrons, and the fact that they never change is wrong. You can have nuclear reactions. Then, the Dalton's atom kind of got interpreted as sort of a, consistent sphere, if you will, where there's no sub particle, I guess is what I would say, subatomic particles. That was one of Dalton's theories of his atom, basically that it was an indivisible atom, that there were no subatomic particles. It was the smallest particle around, and obviously that's wrong. There are subparticles, subatomic particles, the most important of which are the proton, the neutron, and the electron, which were discovered in a variety of experiments in the late 1800s and the early 1900s. So folks tried to explain that. There was something called the plum pudding atom, where electrons were scattered throughout. Through uniform mass, that you had, basically you've got the protons and neutrons were just like the breading and the pudding, and the electrons were the plums. And then the gold foil experiment, where the beta particles were shot through a gold foil, and most of them went all the way through. Some of them were deflected, and some were deflected straight back, gave the idea of the nucleus, where most of the mass and all of the charge, so we have mostly, essentially a mostly empty atom that's composed of a nucleus plus electrons that we don't really know anything about at that point. And then that sort of went to the Bohr model, which was explaining the hydrogen atom line spectra, where electrons orbit the nucleus on a few, very few allowed orbits. And of course, if you were writing this answer, I would think that that being able to include some images is always a good idea. And then the Bohr model goes on to the quantum mechanical model. We still have the nucleus. Now the electrons are treated as waves. We have regions of probable electron density, we call it, that are orbitals. So anyway, I would be looking for you to have touched on 4 of these and some of the things. And this, of course, isn't a very good essay. This is more of an outline of how I would do the essay. And so I'd encourage you maybe to think out, as you're writing an answer to something like this, is think out some of this stuff, get it in kind of a rough order, and then try to write a more coherent paragraph out of it. But the kind of things I would be looking for, again, is that you had 4 of the big models that I identified, and then have what the evidence is, or explaining why one is different from the next one. You can kind of do the evidence both. So anyway, so that's how an essay question might go on a test like this. Again, not sure about how I adapt that to a open book version, but that's something like that. So anyway, so I hope that